Hello students, welcome back to our channel. Students, in this video we are going to discuss topic capacitance from class 12th physics. This is one short video of topic capacitance and we are going to discuss each and every concept of capacitance in this video. Let's start. So what is capacitance? Capacitance is the ability of a body to store charge. We know that every body can store charge, but obviously there will be some capacity of the body to store charge, because body cannot store charge infinitely, right? If this is a body, there must be a capacity of the body that this body can store charge up to this value only. So that capacity of the body is called its capacitance. The ability of the body or the capacity of the body to store charge, that is called capacitance. Now, how the capacitance of a body is measured? Suppose this is a body and we have to measure the capacity of this body. Now what happens when some charge is given to the body? Then potential of the body increases. Suppose this is an uncharged body and some charge is brought from infinity and we have put this charge on this body and this body is now positively charged. So this first step of charging this body was easy because this body initially was uncharged, and to give positive charge to an uncharged body is relatively an easy step as compared to the next step, which is, suppose now the body is charged. Now we have to give this body some more charge. Again, we have brought some positive charge from infinity to give this body. But now this body is already positively charged. So this body is going to repel this excess charge which you are giving this body in step 2. So second step is relatively difficult as compared to the first step, because now we are trying to give positive charge to a body which is already positive. So it is going to repel that positive charge. So more work is required in the second step. So that work is stored in the body in the form of potential. Right, that is the definition of the potential. If in first case W1 work is done to bring a charge of 1 coulomb from infinity onto this body, then the potential of the body becomes W1 according to the definition of potential, because potential at a point is just equal to the work done in bringing a body, bringing a charge of 1 coulomb from infinity to that point. So if in first case we have brought a charge of 1 coulomb and the work done is W1, then the potential of the body is W1. Now in second case, this work done which is W2 to bring another charge of 1 coulomb is obviously much greater than W1, because now we are giving the positive charge to the positive body. So what happens after step 2? The total work that we have done on this body to give it a charge of 2 coulomb is W1 plus W2, and that will be the potential of the body. So we can clearly see as we are charging the body, the potential of the body is increasing, which is making the next step more difficult. So what we want? We want that if we are giving charge to the body, the potential of the body should not increase to a much extent, right? Potential of the body should decrease slowly so that the next step is also easy. Suppose potential of the body is increasing slowly, right? When we are giving more charge to the body, so the potential of the body is increasing slowly. That means that the next step will be easy, because we have to do less work to bring another charge from infinity to this point. So a body is capable of storing more charge if its potential decreases by smaller amounts when some charge is given to it, right? So capacity of a body is given by Q by V. Q should be very large and V should be very small. That body is capable of storing charge more easily and to a much more extent, right? Suppose there is a body 1 which is given a charge of 1 coulomb, and due to that the potential of the body is increased by 5 volt, let us say, right? and there is another body to which we have given a charge of 1 coulomb and the potential increases just by 2 volt. Now we will say that we have to do less work to charge this body, because potential is simply the amount of work which is to be done to store that charge from infinity. So in this case we have to do a work of 5 joule to store a charge of 1 coulomb, and in this case we have to do a work of 2 joule to store a charge of 1 coulomb. So obviously charging this body will take less effort. So when we are measuring the capacity of the body, we are not only measuring the value of Q, but we have to measure the whole value Q by V. So that body is a better capacitor. Capacitor means a body which is specially designed to store charge. So that body is a good capacitor or a better capacitor, in which we have to do less amount of work to store the same value of charge. That's why the capacitance of a body is given as Q divided by V and not only Q. Because if we do not divide this by V and we will say that the value of capacitance is this in terms of Q only. So both these bodies are capable of storing a charge of 1 coulomb. So how will you compare which is a better capacitor? We will compare just by dividing that value by voltage, so that we can get an idea how much work is done to store this particular charge on that body, right? So this is how we can measure the capacitance or capacity of a body. So this formula is very important. Every chapter has a basic equation and all other equations are derived from that. And this is the basic equation of the chapter, capacitance. C equal to Q by V. So all the equations will be derived from this only. So if C is Q divided by V, we can say that Q equal to C into V, and this is another important equation which is obviously derived from this one, and we are going to use this directly also. So what is the standard unit of capacitance? Standard unit of capacitance is, since capacitance is Q by V, then obviously the SI unit of capacitance will be charge per volt, coulomb per volt, right? SI unit of charge is coulomb and SI unit of potential is volt. So the SI unit of capacitance must be coulomb per volt, and that unit is called farad. 1 coulomb per volt is called farad. So 1 farad, which is represented by capital F, is 1 coulomb per volt. Now how we will define 1 farad? So capacitance of a body is said to be 1 farad when the potential of the body increases by 1 volt when a charge of 1 coulomb is given to it, right? So that 1 coulomb per volt is called 1 farad, which is represented by capital F and a very important unit in physics. But this unit farad, let us first derive the dimensions. What will be the dimensions of capacitance? Coulomb, charge is A into T divided by volt. Volt is W by Q. W is ml square T minus 2 divided by Q, that is AT. Now this AT will also go in the numerator, so this is A square T square divided by M L square T minus 2. Now this goes in the numerator, so it becomes M minus 1 A square L square T to the power 4, and this is the dimensions of the capacitor, right? Okay, practically this farad unit is very big. This is such a big unit that it is impossible to have a capacitor of capacity 1 farad. How and why? For that, let us consider a spherical body. So what will be the capacity of the spherical body? We have a spherical body of radius r and some charge Q is given to this body. And if some charge Q is given to this body, obviously the potential at the surface of the body will be 1 upon 4 pi epsilon naught Q by R. So the capacity of the body is C, which is Q by V, Q upon 1 upon 4 pi epsilon naught R. Q se Q cut gaya. So the capacity of the body is 4 pi epsilon naught R, right? Okay. So value of 4 pi, value of this C is what? 4 into 3.14 into epsilon naught 8.85 into 10 raised to power minus 12 into R, right? So 4 into 3 is 12 and 12 into 8 is 96, and this is slightly greater than 8. So this will be approximately, this product will approximately be 100. So if we multiply this by 10 raised to power minus 12, C is close to 10 raised to power minus 10 R, right? So this is the capacity of a spherical plate, spherical capacitor, a body of spherical shape. The capacity of a body of spherical shape is given by this value. So for C to be 1 farad, this R has to be 10 raised to power 10 meter. For C to be 1 farad, this R has to be 10 raised to power 10 meter, and which is practically impossible, because here we are saying that a sphere whose radius is 10 raised to power 10 meter will have a capacity of 1 farad, which is not possible, because you know what is the radius of the earth? Radius of earth is 6.4 into 10 raised to power 6 meter, and this value is approximately 10,000 times greater than the radius of the earth. So imagine a body which is 10,000 times greater than earth. That body will have a capacity of 1 farad. And on earth, we are going to use small capacitors, and the capacity of those small capacitors will be given in microfarad or nanofarad or picofarad. Microfarad means 10 raised to power minus 6 farad. Nanofarad is 10 raised to power minus 9 farad, and picofarad is 10 raised to power minus 12 farad. So those are some practically used units of capacitance. Microfarad, μfarad, nanofarad, NF, picofarad, PF, right? Okay. Now let's come to capacitor. So what is a capacitor? A capacitor is a body which is specially designed to store charge. Body which is specially designed to store charge. Out of all the possible designs, we have a very important and special design, which is the most efficient design of the capacitors, and that is the parallel plate capacitor. So we have to understand the working of parallel plate capacitor. Here we have a parallel plate capacitor. A parallel plate capacitor has two metallic plates which are connected parallel to each other, and there is some dielectric medium between the plates. That dielectric medium serves many purposes. One is to give support to the plates, right? We should have something between the plates so that these plates can be attached to that thing, and which functions as a supportive thing to support these plates. So there is some dielectric between the. Dielectric is simply insulator. There is a slight difference between dielectric and insulator, and we will discuss that point later in this video. But let us say that dielectric means insulator. So there is an insulating or dielectric material between the plates. But right now, just to understand the working of this capacitor, let us assume that it has air between the plates, right? Okay. So now this plate is connected to, one of the plates is connected to the positive terminal of the battery, and the other plate is connected to the negative terminal of the battery. So what happens, since this is the positive terminal and this is the negative terminal, so these terminals start attracting electrons from this plate, and electrons start moving in this direction like this. Right? And this is negative terminal, so this terminal starts giving electron to the other plate of the capacitor like this. So with time, this plate, since it is losing electrons, this plate starts acquiring positive charge, and this plate, since it is gaining electrons, it starts acquiring negative charge. Now let us say the potential difference between the terminals of the battery is V. So this process will continue until the potential difference between the plates of the capacitor also becomes V. Obviously, because charge flows only when there is some potential difference. So this plate is continuously increasing its positive charge, and the negative charge of this plate is also being continuously increased. So the potential difference between the plates will increase, and obviously since this battery is responsible for charging this capacitor, so this potential, the potential difference between the plates of this capacitor cannot increase beyond V. So after some time, when the potential difference between the plates become V, this process stops, and in that case the charge flowing through these wires also stops. When the potential difference between the plates of the capacitor, become V. So now this plate is fully positively charged and this plate is now fully negatively charged. Now let us take the charge on this plate as capital Q and charge on plus Q, and charge on this plate is minus Q. Now the equilibrium is attained and no further charging of the plates will take place. So in this case, after this scenario, the charge will stop flowing through the wires and this capacitor will behave like it has blocked the flow of charge, because now it is fully charged. So what happens, suppose if the small bulb was attached in this circuit, and this charging of capacitor process, this process takes fraction of second. This whole process takes less than 1 second. So what happens? You have connected an uncharged capacitor with a battery. Now when the switch is on, this bulb will glow just for a fraction of second and then it will go off. Why is it happening? Because the charge is flowing in these wires till the capacitor is getting fully charged. Once the capacitor is fully charged, no further charge will flow through the wires and the bulb will not glow, right? Okay, so if the capacity of this capacitor is C and the charge on one plate is plus Q and charge on other plate is minus Q, and the potential difference between the plates is V in the steady state, then these three are related as Q equal to C into V. Kindly note that the charge on the capacitor is taken as Q and not 0. You can easily say that the charge on one plate is plus Q and the charge on other plate is minus Q, so the total charge on the capacitor should be 0. But that is not the case. If obviously if the total charge on the capacitor is 0, so what has it stored? It has not stored anything. But since it is charged, so what is the charge on the capacitor? This Q value, this Q, ignore plus Q and minus Q, this Q is the charge stored by the capacitor, C is the capacity of the capacitor, and V is the potential difference between its plates. So Q equal to CV. These three variables are related like this. So let us quickly revise this whole process. Electrons from plate A, where is the plate A? This is the plate A and this is plate B, right? So electrons from plate A move from plate to battery due to attraction of negative terminal, due to attraction of the positive terminal, sorry, not the negative terminal, due to attraction of the positive terminal. Due to this action, plate gets positively charged. Electrons from negative terminal of battery move to plate B. Due to this action, plate A acquires negative charge. Plate B acquires negative charge. Now, important points to note. This is very important. Charge acquired by one plate is always equal and opposite to the other plate. That is, if the charge acquired by one plate is plus Q, then the charge acquired by the second plate should be minus Q. The potential difference across the plates of the capacitor become equal to potential difference of battery in fraction of seconds after connecting, and charge on capacitor is then taken as Q and not 0, and the capacitance of the capacitor is C, which is Q by V. Clear? We have discussed all these points. Now let us find the formula for the capacitance of a parallel plate capacitor. Now here we have a parallel plate capacitor, and one plate of this capacitor is positively charged. Let us say this plate is positively charged and this plate is negatively charged. Obviously, whenever there is one positive plate and other negative plate, so there must be an electric field. So there is an electric field E between the plates of this capacitor. Now all the parameters are given here. V is the potential difference between the plates. We know Q is the charge on the plates. E is the electric field between the plates. Sigma is the surface charge density. What is surface charge density? If A is the area of each plate, A is the, we have not written it here, but we have taken this A. A is the area of each plate. I'll write it here. A is the area of each plate. So sigma is called the surface charge density, which is charge per unit area. So sigma is Q divided by A. That is surface charge density, which was a very important parameter in last chapter. So C is Q by V, and Q is what? Q is sigma into A. Now if we put this sigma into A in place of Q, so this becomes sigma into A by V. And since V equal to ED, from the concept of potential gradient, we all know that if the distance between the plates is D and this electric field is E and the potential difference between the plates is V, then these three are related as E equal to V divided by D. So V is E into D. So V is E into D. So in place of V, we have written E into D. And from Gauss theorem, we know that if these are two plates, one is positively charged, one is negatively charged, then the electric field between the plates E is given as sigma by epsilon naught. So in place of E, in that formula, we will, in this one, in place of E, we are going to put sigma by epsilon naught. So sigma se sigma cut gaya. C is epsilon naught A by D. So this is a very important formula for parallel plate capacitance. Capacitance of a parallel plate capacitor is epsilon naught A by D. And if there is some medium between the plates of the capacitor, now there is some dielectric. So there is some dielectric between the plates of the capacitor, and the dielectric constant of this is K. So the capacity is, because we have taken epsilon naught just because we have assumed that air is between the plates, but now if there is some medium between the plates, then we have to take K epsilon naught and not epsilon naught only. So in place of epsilon naught, we have to write K epsilon naught. So if there is some medium between the plates of the capacitor, then the capacitance of capacitor is K epsilon naught A by D. So simply the capacitance of a capacitor, of a parallel plate capacitor, is directly proportional to the area of the plates, and it is inversely proportional to the distance between the plates. If the plates are closer, then D decreases and D decreases, so C increases, so capacitance will increase. And if the area of the plates will increase, then obviously again the capacity will increase. Right? energy stored in a capacitor. Now when we are charging the capacitor with the help of a battery, so battery is doing some work to charge the capacitor. So obviously that work is stored in the capacitor in the form of some kind of energy. That is the electrical potential energy stored in the capacitor. So how to derive the formula? Now let us say at any instant, not in the final instant, at any instant in between when the capacitor is not fully charged, let us say the charge on the plates is Q. So the potential difference between the plates V is given by Q by C. Q by C. So small amount of work done to store additional charge dQ on the capacitor. Small amount of work done by the batteries to store initial charge, extra charge, sorry, not the initial charge. We are considering a situation when the charge on the plates of the capacitor is Q. So from that situation, the additional charge stored by the battery on the capacitor is dQ. So for that, the work done by the battery is dW, which is given as dW equal to V into dQ, because the potential difference between the plates of the capacitor is V. So now in place of V, let us put Q by C. So in place of V, we have put Q by C, and the total work done to store the total charge, capital Q, because the total charge is capital Q, is the integration of this. So the integral of dW becomes W, and Q by C में से 1 upon C is constant, तो उसको बाहर ले लिया हमने. Now it is Q dQ. So the power of Q is 1. Now if we use the concept of integration, integration of x raised to power n dx is what? X raised to power n plus 1 divided by n plus 1. So this becomes Q square, Q to the power 1 plus 1 by 1 plus 1, that is Q square by 2. Then upper limit, which is capital Q, minus the lower limit, which is small q. So the final result for the work done is this, and this is the total work that the battery will do to store the total charge, capital Q, on the plates of the capacitor. And this work is stored in the capacitor in the form of some kind of energy, and that energy is electrostatic potential energy, Q square by 2C. Electrostatic potential energy, Q square by 2C. So this is one formula for electrostatic potential energy. Now since Q is what? Q is C into V. So in place of Q, if we write C into V, so this is C square V square by 2C. एक C से C कट जाएगा. Then another formula for energy is half CV square. This is also very important. And we know that C is Q by V. So in place of this C, if we put Q by V, एक Q से Q cancel, this V will go in numerator. So half QV. These three are very important formulae to find the energy stored in a parallel plate capacitor. U is energy stored per unit volume. Now energy density. What is energy density? Energy density is represented by small u, and energy density is the energy stored in the capacitor divided by the volume of the capacitor, that is energy stored per unit volume. So this is a capacitor. And the distance between the plates of the capacitor is D, and area of each plate of the capacitor is A. Then the volume of the capacitor is obviously A into D, right? So energy stored per unit volume is called energy density. When we use the word density, it means that we are dividing by volume, right? When we say density, so we mean mass density. But if mass density means mass per unit volume, so but if we are talking some other kind of density, then we have to mention. So energy density is energy stored per unit volume. Energy stored in the capacitor is half CV square. This is the formula, half CV square divided by AD. And C we have just derived that it is epsilon naught A by D. And V by the concept of potential gradient. We have already discussed this formula, V equal to E into D. So in place of this V, we have put E into D. So V square becomes E square D square. So here we have 2 D's and 2 D's, 1A and 1A. ये सब cancel हो गया. So energy density is half epsilon naught into E square. Half epsilon naught into E square. Right? Okay. Dielectric polarization. What is dielectric polarization? In the beginning, I said that there is a slight difference between a dielectric and an insulator. So what is that difference? We will study a very important process which is called dielectric polarization. Suppose this is a capacitor, so one plate is positively charged and the other plate is negatively charged. And between the plates of this, suppose we have placed a slab of a dielectric material like this. So what is a dielectric material? Okay. A dielectric is an insulator which gets polarized when it is placed in an external electric field. A dielectric is an insulator which gets polarized when it is placed in an external electric field. But what is the meaning of this statement? Polarized. There are two types of insulators. One is called the polar and one is non-polar. For example, HCl is a polar molecule because H and Cl both have different electronegativity and Cl is more electronegative as compared to H. So what happens? The electrons of this bond are shifted slightly towards Cl, so it gets a partial negative charge and H gets a partial positive charge. So positive negative poles are created. That's why it is called polar. But if the electronegativity of these two atoms, this is a polar molecule. But if the electronegativity of these two atoms is same, here we have A and B have both same electronegativity. So the electrons of this bond will stay in the middle, because electronegativity is simply the property of an atom to attract the shared pair of electrons towards itself. But if the electronegativity of A and B is same, then these electrons will stay in the middle. So neither A nor B will get any charge, positive or negative. So such kind of molecule which is obviously unpolar because there are no positive and negative poles, these are non-polar molecules. Now what happens if a material of this type of molecules, which has this type of molecules inside it, that material, slab of that particular material is placed in an external electric field. Now here we have an external electric field E. So what happens? The electrons of this, which was otherwise non-polar, gets attracted towards the positive plate, right? If there is a positive plate on this side and a negative plate on this side, so what happens? The electrons of this bond will shift towards the positive plate because electrons are negatively charged, so they will be attracted towards the positive plate. So the molecule which was otherwise non-polar will get obviously polarized when it is placed in an external electric field, because when the electrons get shifted towards A, now this A get a slightly partial negative charge and this gets a partial positive charge. So this becomes negative and this becomes positive. Now what happens? The molecule which is lying beside this the electrons of that molecules will be attracted towards this positive, so this end will become negative and this end will become positive. and same thing happens with this molecule also, and same thing happens with all the molecules. So this positive will cancel the negative of this molecule, this positive will cancel the negative of this molecule, this positive will cancel the negative of the next molecule. All these positive negatives will be cancelled and we will left with a negative charge of this end of all the molecules at this end of this slab, and positive charge of the last molecule because this negative is not going to get cancelled with some any positive, because this positive is cancelling the negative of the neighboring molecule and this positive is cancelling the negative of the neighboring molecule. So this negative is left for each molecule and this positive is left, which means this end of this slab is positively charged and this end of the slab is negatively charged. So two opposite poles are created in this slab. So a dielectric which was otherwise non-polar, when placed in an external electric field, gets polarized, and an electric field is induced in the opposite direction to the external electric field, right? Because electric field is always from positive to negative, and in the capacitor, in the plates of the capacitor, this plate was positive, this was negative. So the direction of external electric field was like this. Let us take this external electric field as E naught, and direction of internal electric field will be opposite to this, because from positive to negative, if we'll make this internal electric field, it will be like this. So let us take this electric field as EP, and obviously there will be impact of this electric field also. So the net electric field inside this becomes E, which is E naught minus EP. Net electric field inside this dielectric becomes E naught minus EP. Now if the dielectric constant of this dielectric is K, that K is given by E naught by E, so which means E is E naught by K. That is a very important definition of, another very important definition of the dielectric constant. Suppose the dielectric constant of a dielectric material is 2, which simply means that if this dielectric is placed in an external electric field of 10 microcoulomb, Newton per coulomb, if the dielectric constant of a dielectric is 2, it means that if this dielectric is placed in an external electric field of 10 Newton per coulomb, then the net induced electric field inside the dielectric will be 10 by 2, that is 5 Newton per coulomb. Right? So this is an important phenomena of dielectric polarization. Dielectric polarization. So we have a very important derivation in which we are going to find the capacity of a capacitance in which, between the plates of which a dielectric slab is placed like this. This is a capacitor and the distance between the plates of this capacitor is D. And the thickness of this slab is T. Right? Distance between the plates of the capacitor is D and the thickness of the slab is T. And the external electric field is E naught. And this plate is positively charged and this plate is negatively charged. And the field inside is E, which is E naught by K, and dielectric constant of this capacitor of this dielectric is K. So this field inside the capacitor E is E naught divided by K. Okay, now we have to find the capacity of this capacitance. initially the capacity was, when the slab was not inserted, the capacity was C naught and it was epsilon naught A by D. This formula we have already derived. So since V is E into D, right, V is E into D, so if we take total potential difference from this plate to this plate, then that potential difference is E naught into D minus T, because for this part, for D minus T part, electric field is E naught, and for T part electric field is E. So V is E naught into D minus T plus E into T. And if in place of E we put E naught by K, in place of E we put E naught by K, so V is E naught into D minus T plus E naught by K into T. Now let us take E naught as common. So E naught into D minus T, E naught into D minus T plus T by K. Now the new capacity will be given as C dash, which is Q by nu V, and this is the new V. So let us put this value in place of V, Q by E naught into D minus T plus T by K, and since this E naught is what? One step is missing, I'll just write that step. Q divided by this E naught is, we already know it is sigma by epsilon naught. And sigma is Q by A. Next step is this. कहाँ लिखूं मुझे? I should have written this here. C dash is Q divided by sigma by epsilon naught D minus T plus T by K. And since sigma is Q by A, so C dash is Q upon Q by A into epsilon naught D minus T plus T by K. So this becomes epsilon naught A by D minus T plus T by K. This is the final result. Now let us compare which is greater. Initially the capacity was epsilon naught A by D. When we have inserted the slab, the capacity is epsilon naught A by D minus T plus T by K. So which one is greater? Numerator of both of these is same, epsilon naught A. Denominator of that is D, and denominator of this one is D minus T plus T by K. Now something is being subtracted from D. So obviously this part of the denominator is lesser than that part, but something is again added with the denominator. So which is more? The thing which is getting subtracted is more, or the thing which is the term which is getting added is more? Obviously this one is more, because this is T by K and K is always greater than 1. Because K is what? K is epsilon naught by E. Sorry, E naught by E, and E naught is always greater than E, because E is induced due to E naught, na? So E naught is the inducing field and E is the induced field, so induced will always be less than the inducing field. So K is always greater than 1, because numerator is more than the denominator. So if T is being divided by something which is greater than 1, then obviously T by K will be less than T. So we are subtracting a bigger term and we are adding a smaller term, which makes this overall less than D. So numerator of both of these is same, but the denominator of this one is smaller than this. So C dash is greater than C naught, which means when a dielectric slab is inserted between the plates of the capacitor, when the dielectric slab is inserted between the plates of the capacitor, the capacitance of the capacitor increases. Clear? Okay, now let us insert a conducting slab between the plates of the capacitor. Now let us say that this slab is conducting. Overall the diagram is same, but now this material is not dielectric, this is conducting, right? So what happens? We all know that the electric field inside a conductor is 0. So the total potential difference is V E naught into D minus T plus E naught into D minus T plus E into T, and the value of E is 0. So V equal to E naught into D minus T. Now in place of E naught, let us put sigma by epsilon naught. So V is sigma by epsilon naught into D minus T. C dash is Q by V. So in place of V, let us put this sigma is Q by A. Now in place of this V, let us put Q by A epsilon naught into D minus T. So Q से Q कट गया, epsilon naught A will go in the numerator. So it is E naught A by D minus T. And initially the capacity was epsilon naught A by D. यहाँ ज्यादा दिमाग लगाने की जरूरत नहीं है. We can clearly see that the denominator of this is smaller than this and even smaller than the other one, the dielectric one. So we can say that the capacity is maximum in case of conducting slab, right? Conducting slab डालने पे capacity is maximum. फिर dielectric slab, and फिर free space between the plates, that is air or vacuum. Okay, so otherwise the capacity of the capacitor is least when there is free space, that is air or vacuum between the plates. When the dielectric slab is inserted, the capacity slightly increases, but when the conducting slab of the same thickness is inserted between the plates of the capacitor, then capacity is much higher. Okay, now in this case, let us take a special case when this D becomes equal to T, यानी कि हम पूरा फिट करके we are inserting the slab. When this D becomes equal to T, thickness of the slab becomes equal to the distance between the plates. Now this D minus D, this C dash becomes epsilon naught A by D minus D plus D by K. D से D कटा. What is the final result? C dash is K ऊपर चला गया, K epsilon naught A by D, which is same, which we already know that if there is some material of dielectric constant K between the plate, then the capacity of the capacitor is K epsilon naught A by D. And here, if D is equal to T, in case of conducting slab, if D is equal to T, what happens? C dash becomes epsilon naught A by 0, that is infinity. The capacity becomes infinity, which doesn't mean that capacitor is going to store infinite amount of charge. It simply means that now, since the plates were already conducting and this slab is touching the plates, so this is a whole block of conductor. So this is going to get charge from this plate or this end, and this will throw away the charge to the other end. So it is acting like a conducting plate and not storing. It is acting like a conductor. It is letting the charge flow through it and it is not storing the charge. So we will get a feeling that we are giving it an infinite charge, and it is taking charge again and again, continuously taking the charge without getting full. Combination of capacitors. Combination of capacitor means if we do not have a single capacitor of the capacity that we need, we will connect the capacitors in series and parallel, exactly equivalent to the combination of resistors that you have studied in class 10th. Now let us say we have connected 3 capacitors in series. कहाँ बनाऊं? ओके, यहां पे बनाते हैं, थोड़ा बड़ा चाहिए बिकॉज now here we have 3 parallel plate capacitors connected to this battery of V volt. Now let us say the charge given by this battery is plus Q and the charge given by this terminal of the battery is minus Q. So the plus Q charge is stored here and the minus Q charge is stored here. And we know that the positive charge on one plate of the capacitor is equal in magnitude to the negative charge on other plate of the capacitor. So if this plate stores charge plus Q, this plate stores charge minus Q. Now, this is very important. Now this is what? These two plates are a system of these two plates are a system of two plates, which is an isolated system because these two are connected to each other, but they are not connected to any external supply. And charge on an isolated system always remains conserved. That is the law of conservation of charge. So if a minus Q charge is induced on this plate, then plus Q charge has to induce on this plate, and minus Q charge will be induced on this plate, and these two are again isolated system of plates, so plus Q charge will induce on this plate. So we can clearly see that charge in series is same on every capacitor, and that is the main take from this topic, that charge remains same when the capacitors are connected in series, and the capacity of this is C1 and capacity of this is C2 and capacity of this is C3, and we know that Q is CV. So Q is same for everyone and C is different for everyone. Then obviously V is going to be different for each of these capacitors. So capacity between the plates of potential between the plates of this capacitor is different, between the plates of this capacitance is different, and between the plates of third one is different. Now let us say the potential between the plates of this capacitor is V1, potential between the plates of this capacitor is V2 and V3. And since this is V, then obviously let us take the positive terminal is at V potential and the difference is V. So the negative terminal will be at zero potential. And since there is no component from here to here to here, so this point will also be at V potential and this point will be at zero potential. So the total potential difference between all these three capacitors is what? It is V. Now, so the V is what? V is V1 plus V2 plus V3, and since V is Q by C, so it is Q is same. So V is Q by C1 plus Q by C2 plus Q by C3. Now, if C is the equivalent capacitance, what we are looking for? We are looking for a single capacitor which was connected in place of these three, will give us a capacity C equivalent. So obviously the charge stored by that single capacitor will again be Q, because it is connected in place of these three capacitors and it is connected to the same battery. That is the condition ना. Equivalent capacitance का मतलब है कि if इन तीनों की जगह एक single capacitor लगा होता, such that that single capacitor is also extracting the same amount of charge which this combination is extracting. So what will be the capacity of that capacitance? So obviously it is extracting the charge Q from the battery, and a single capacitor is placed in place of these three. So the potential difference between the plates of that capacitor is V. So we can write Q by C equivalent is Q by C1 plus Q by C2 plus Q by C3. Q कॉमन आ गया, Q से Q कैंसिल, 1 अपॉन C इक्विवेलेंट इज 1 अपॉन C1 प्लस 1 अपॉन C2 प्लस 1 अपॉन C3. So this is the formula to find equivalent capacitance when the capacitors are connected in series. So if these were three capacitors, so if we have two capacitors, so C equivalent is 1 upon C1 plus 1 upon C2. Now if we take the LCM and do the reciprocal, we will get C1 C2 by C1 plus C2. You can remember this formula directly because this one will help you to do the questions quickly, because in many cases you always get two capacitors. So just quickly write C1 C2 by C1 plus C2 to find the equivalent capacity. And if all the capacitors are identical and n capacitors of capacity C are connected in parallel, in series, sorry, then the equivalent capacity is 1 upon C plus 1 upon C plus 1 upon C up to n times, right? So that will be n upon C. So the reciprocal of that will be C upon n, right? For example, if 10 capacitors each of capacity 20 microfarad are connected in series, so what will be the equivalent capacity? That will be 20 by 10, that is 2 microfarad. Parallel combination. Now in parallel combination, three capacitors, let us say three capacitors, we can derive the formula for any number of capacitors. Now three capacitors are connected in parallel तीन कैपेसिटर्स लगे हैं ऐसे parallel में. Parallel combination means that one end of each capacitor is at same point and the other plate is also at the same point. So these three plates of the capacitors are at point A and these three plates of all the capacitors are at this common point B. Now if the potential difference is V of the battery, so this positive part is at support V potential and this is at zero potential. Since there is no component from here to here, so this point is also at V potential, at this point is also at zero potential. So the potential difference between all three capacitors is V. Now if the capacity of this is C1, capacity of this capacitor is C2, capacity of this capacitor is C3, and the charge given by the battery is Q. So this charge will be divided in three different parts because it will get three paths, and the charge will be distributed according to the capacities of the capacitors. If the capacity of C1 is higher than C2 and C3, then the charge Q1 will be higher than Q2 and Q3. And so the total charge, which is Q, is Q1 plus Q2 plus Q3. Now in series, charge was same on every capacitor, and in parallel potential difference between the plates of every capacitor is same. So if there was a single capacitor in place of these three capacitors and the capacity of that is C equivalent, so the potential difference between that single capacitor, potential difference between the plates of that single capacitor is V, and the charge stored by that capacitor is Q, because the combination is extracting this charge Q from the battery. So Q is C equivalent into V. So in place of this Q, we will write C equivalent into V. In place of Q1, we will write C1 into V, because V is same for every capacitor. And in place of C2, we will write C2 into Q2, sorry. In place of Q2, we will write C2 into V, and for Q3, we will write C3 into V. V common आ गया, V से V कट गया. C equivalent is C1 plus C2 plus C3. Which is very simple. Capacity is simply added up when the capacitors are connected in parallel, right? So capacity is more than the capacitor with the highest capacitance. So when the capacitors are connected in parallel, capacity increases, and when the capacitors are connected in series, the capacity decreases, because this answer is going to be smaller than the smallest of C1, C2, C3. For example, let us take the value of C1 is 1, value of C2 is 2, and value of C3 is 3. So 1 upon C equivalent is 1 upon 1 plus 1 upon 2 plus 1 upon 3 LCM is 6. This is C equivalent is 6 divided by 11, which is approximately 0.54. Suppose these three were in microfarad, so 0.54 microfarad will be the equivalent capacity, and the smallest of these three was the capacitor of capacity 1 microfarad, and the result is even smaller than that. So when we have capacitors of bigger value but we need smaller value in the circuit, we connect those capacitors in series, and when we have capacitors of smaller value but we need a bigger capacitance in the circuit, we connect them in parallel. So this was complete topic of capacitance. You have to prepare each and everything very carefully. I'll meet you in the next lecture. Till then, all the best.